what he has to say. Okay, so it is there in lecture 5. So I'm going through that one, and then I'll go to the notes, which I'll describe something. So this is part of Riemann's paper. So what he defines here, yeah. So the concept of definite integral and the range of its validity. So that's what he actually called this section, and he defined integration as we did here. Certainly, we will not go into the definition. What we will go is towards what functions are Riemann integrable. So, as I mentioned here in this section, Riemann defined what the integration means, and he also commented on the earlier work. So he was quite familiar with the work of Bossi, who gave the definite concept of definite integral for continuous functions on sudden smooth function, piecewise continuous, this kind of stuff. Of course, but their theorems, it is not generally doesn't hold for general functions. So once he defined the Riemann integration, as we mentioned in our lecture, so then he asked this question: in which cases? So this is the one. See here, this green one. So in which cases can a function be integrated, and in which cases can it not? That means what are the class of Riemann integrable functions? And let us see how he goes towards that. So here he writes, we consider first the concept of integral in the narrow sense. That is, we suppose that the sum is converges if the deltas together become infinitely small. Well, that is fine. Delta is the length of the partitions, each of the length of the subintervals after the partitions. Now he introduced one term, which is fluctuation. So in a small interval, subinterval, function can fluctuate, right? The greatest fluctuation means supremum of the function minus infimum of the function. That is actually the fluctuation. We'll make it formal. But let's see what Riemann gave it these things around 1850, which is around 170 years back. Right. And so that is what he called fluctuation. We now call that one as oscillation. So now he looked at these fluctuations, and the length of the subintervals as a sum, right? Like this. And this must become infinitely. This must become small. This is nothing but the upper sum minus the lower sum, right? We looked at supremum minus infimum together in terms of in this one, in these quantities. We looked at this quantity, we put supremum minus infimum together, and these are the length of the subinterval, subintervals. Now, so this one wants this to be small when epsilon deltas become smaller. Now he talks about the greatest value it can take as delta. This sum can reach as long as delta smaller than some number d, which we now call epsilon. Then this will become function of epsilon and a function of d in this case, and you get this. Now, one important thing here: the total length of the interval in which the fluctuations, sometimes fluctuations, which means that the supremum minus infimum can become bigger, sometimes it can become smaller. Now, here is an important remark. This total length of the intervals in which the fluctuation is greater than sigma. So, where supremum of f minus infimum of f is greater than sigma, look at those subintervals and then try to see what happens. So this sum, so look at contribution of those intervals only, where the fluctuation is greater than this. Now this total sum will be greater equal to sigma times the length of the subintervals, sum of the length of the subintervals, and here one gets this one. So now important thing is there. Yes, what is S? S is here. See, this is the S. The total length of the intervals in which the fluctuation is greater than sigma. So this length has to be small. The point is, given sigma, this can always made arbitrarily small by suitable choice of d. So the point is that this can be made very small. So here what it says, in order for the sum to converge where the deltas become infinitely small, in addition to f being finite, f of course f has to be finite. If f becomes infinite, then there is nothing to be done. It is necessary that the total length of the interval in which the fluctuation exceed this number sigma can be made arbitrarily small. So now remember, where the point of discontinuities, where there is a point of discontinuities, so you in around that point of discontinuity, you make the interval arbitrarily small. That is what it's coming again, right? Now there is nothing, no talking about continuity, but what it says, it says about fluctuation, right? So if it is continuous, there will be no fluctuation as such. Fluctuation can be made very small, taking the length of the subinterval to be smaller, right? But if there is a discontinuity, there is a fluctuation. That is the point. So here, what he is trying to give a necessary condition about the point of discontinuities. Whether there is a fluctuation, then what happens? The points you take and you cover by small intervals of those points, then some of the intervals must be very small. That is what the point is. Right? Is it clear? Okay, let's look at the next one. So then,
Sir,
yes.
so if the function is continuous, we will be able to ensure that there is no interval in which the fluctuation is greater than sigma for any given.
Right. That's
But if
possible,
it's not
yes.
continuous, we can't ensure that, but we can still ensure that the interval itself is very, very small.
We have to ensure for integrability. You can't
Right.
ensure all the time. For example, you look at Dirichlet function, you cannot ensure that.
Which function?
Dirichlet function.
Ah,
So
right.
zero at one at irrational, one at rational, and zero at irrationals. So you cannot do that. right? The point is for integrability, one need this one. So this is a necessary condition what Riemann gives. Almost precise, right? And around 170 years back, what the exposition he has given is almost precise. Of course, that time epsilon delta was not there. But yeah, right? So you have
Sir,
to make sure, yes.
sir, are these the only two conditions for integrability? That is boundedness, and if there is a discontinuity, the interval can be made arbitrarily small.
So if there are multiple discontinuities, then
Arbitrarily small around all discontinuities. I mean,
oh no. You have to look at you have to cover those points of discontinuities by small intervals. And some
it's
of
so
those interval total length has to be very small.
okay, okay,
Some total of the length where
okay.
there is a there is a point of discontinuity. So suppose this is a point of discontinuity. So you put uh, you make a small interval, and then it is there discontinuity is there maybe somewhere else also. You consider all those small intervals, look at the sum of the lengths that you need to make small. Is it clear now?
Yes, sir. Yes, sir.
Yeah, so that is the main point of integrability, Riemann integrability, as you see from Riemann's paper itself. All right, so let's look at the next one. Yeah, so clearly says that if the function is always finite, which means bounded. So here, by infinitely decreasing the delta, so deltas you make smaller and smaller. Total length is of the intervals in which the fluctuation of the function is greater than a given number always becomes infinitely small. This is what I mean, right? There, I mean, there is where there is a fluctuation greater than this one, which means you have a point of discontinuity. Right, infinitely small, then the sum converge as this becomes small together. So that was kind of uh, yeah. Yeah, right. So this is what other side, right? So once you can make this where the fluctuation is less than if is arbitrary is small, then the sum will also converge because at other points you have this fluctuation less than any number, right? Given number. That's what he mentioned then, right? So here what he argued is sufficiency of the condition above. So what is the condition? Condition is so for every point of discontinuity, you put a small subinterval and look at all the subintervals. So that means subintervals gives you a cover, right, of the point of discontinuities. Now you can make that sum total of the lengths of the subintervals less than epsilon, less than delta or whatever, very small, right? So that is the most important part. So that is the property what we need, and that property is the beginning of the Lebesgue's integration, Lebesgue's theory of measure and integration. Okay, so we now look at the more formal things. So formalizations. Notes are uploaded, so you can see these things there as well. So here, so we want to formalize. So the fluctuation, as I said, fluctuation is supremum minus the infimum, right? And you take a partition, and dj will be the fluctuation on the small interval, this. Now, in our notation, dj is just capital Mj minus small mj, right? And delta j is just xj minus xj minus 1. Therefore, the sum that Riemann considers is the usual sum, right? UPF minus LPF. So Riemann wanted the above sum to be sufficiently small, right? So we want also that one, that that this sum has to be sufficiently small. So which means for every epsilon there exists a partition such that this one is less than epsilon, right? So this one, of course, this depends on the partition, and this characterization for every epsilon there exists a partition such that this one comes right from there, right? So that is what actually was noticed by Darboux. So upper sum minus lower sum was not given in Riemann. Riemann gave this one, but you see it is very clear from the Riemann's definition, right? Once you make things formal, once you know epsilon deltas things. Now the point is, so I mentioned here again this part, small part. This S has to be less than some. I mean, the S has to be very small, right? So that is what we. That is what is very important. Again, I'm focusing on that. Yeah. So let me now give the more formal definition, what it means. So theorem, let f from AB to R be a bounded function. F is Riemann integrable if and only if the set of discontinuities let's say discontinuities is, let's call it script T of F satisfies the following property. So the property we will call property star. For every epsilon greater than 0, there exists a collection Uj, j from 1 to infinity of open intervals such that the script D will lie in the union j equal to 1 to infinity uj, and secondly the sum of the length j from 1 to infinity l uj, this is the length of the length of the interval uj. The sum is less than epsilon. All right. Yeah. So this is the sufficient condition. that the point of discontinuity satisfies this property. So is it clear, the statement? Yeah. So this is the if and only if condition for Riemann integrability. So whatever you will find the book, you will find some sufficient condition, but the most general thing is here. For the proof, you need, of course, the proof, as Riemann pointed out, proof will be going into that lines. But I don't want to keep the precise proof right here. Now online, as I mean, it is quite long and more calculative. Uh, Calculative in the sense like this, you need to look at covers and a lot of stuff. So it is there in the notes, the part 6 of the notes. So you can look at the proof, and we'll have an interaction session about this thing. Okay, about just the integrability condition. So the first point is whether the statement is clear or not. So maybe I'll define something which is beyond this course. A subset S of R is said to have the Lebesgue measure 0 if it satisfies property star. So we don't want to define what is Lebesgue measure, but the point is the Lebesgue measure is the length of the interval if the set is an interval. So, and this concept here is what is called Lebesgue measure 0. So the proof, of course, the hint of the proof lying inside the Riemann's proof, or Riemann's argument, but there one can define Lebesgue measure and whole theory of integration built up around 1902 by Lebesgue. So the point is, the first thing is whether this statement is clear. The statement of the theorem is clear or not. Yeah? So is it clear? Once you know this theorem, then you can actually characterize the functions which are integrable quite easily. Now you look at this function, which is Dirichlet function, which is 1 at the rationals and 0 at the irrationals, and you will see your set of discontinuities is whole interval. So you cannot do the sum of the interval will always be b minus a. So you cannot make it epsilon, right? Yeah. Any question here?
So could you repeat once why the set of discontinuities for the Dirichlet function will fail to satisfy star?
Yeah, because of this reason, because of this reason. So what is, let me look at that example. Yeah. So consider fx to be 1 when x is rational and 0 when x is irrational. All right. Now what is the well you intersect with an interval AB. right? You intersect with an interval AB. Now the points of discontinuities. What are the point of discontinuities of F? Can you tell me what are the point of discontinuities?
All rational.
What about irrationals? Is it continuous?
No, they are also rational.
Right. So the whole thing, right? So the length of this is B minus A, right? Suppose Uj is a collection of open intervals such that AB contain in union J from 1 to infinity Uj. That implies summation length of Uj J from 1 to infinity must be greater or equal to B minus A, right? Which is length of the interval AB, right? Because this lies inside, right? Is this fine?
Right, sir. Got it.
Right? So you cannot make it small, cannot make it less than epsilon, right? So this cannot be, so this cannot be done, right? Yeah?
Right.
Yeah. So,
Sir,
yes.
sir, in case of any infinite discontinuities, can we do it? Like
Yeah.
if the number of discontinuities are infinite, then it is bound to be greater than some value.
No, 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 no. The point is you can actually, let's look at function which has discontinuities, let's say,
So
suppose.
countably infinite discontinuities we can do, uncountably infinite we can't, I guess.
No, you can do uncountable discontinuities also. So do you know, have you heard about Cantor set?
Thomas function.
Yes, what function?
Thomas function.
What is Thomas function?
Uh, b- uh, if x is a rational of the form a by b, then it gives 1 by b, and it gives 0 at rationals.
Zero irrational. So you
So
get
that it's integrable.
right. So you get what are the points of discontinuities?
It's discontinuous at all irrationals and continuous at all rationals, I guess.
No, no, no.
No, it's discontinuous at all rationals and continuous at all
Right,
irrationals. Yeah.
right,
Mm-hmm.
right. So you so how do you define the function? So example 2, let's say. So you define the function f(x) equal to 0 if x belongs to r minus q, right?
Yes, sir.
This is 1 by q
1 by b. Okay, 1 by q if x equal to p by q, where p
p
and
by
q are the lowest terms.
yeah. So and this is in q and p by q are co-prime to each other, right?
Yes,
So
sir. Copen.
yeah, right. So this is the reduced form. This is x in p by q in reduced form. Right. So the points of discontinuities. So let's look at an interval intersection with AB, and this is Q intersection with AB. I also discontinuities is equal to this Q intersection AB, right? Yeah. The point is here Q is countable, so hence you can enumerate, right? So since Q is countable, you can enumerate, say, x1, x2, so on, right? Now, around each xj, so consider uj to be xj minus epsilon. So given epsilon, so we take given epsilon. So consider xj minus epsilon by 2 to the power n. 2 to the power j, or maybe 2 to the power n is fine. Right. xj my plus epsilon by 2 to the power n. N is as large as we can choose, right? Look at this interval. All right. Or if you would like that this will be also fine, just put j. Let it depend on j. Right? Then Q intersection. So Q intersection AB, not just Q. Q intersection AB. Now Q intersection AB is covered by union of uj, j from 1 to infinity, right? So this implies length of Q intersection AB. But we don't need length of this one. Rather, we want this length of uj. What is length of uj? This is, or maybe let's put 2j plus 1 to make it even easier. So epsilon by 2 to the power j. Now look at sum. J equal to 1 to infinity. Sum j equal to 1 to infinity. So what will be it? Epsilon, right? Yeah. Is this fine?
Yes, sir.
So you can make, so this, the point of discontinuities, of f satisfies star, right? Yeah. Now even this point of discontinuities are countable, right?
Yes, sir.
Yeah. What if the point of discontinuities are uncountable? So does there exist, the question is, does there exist an uncountable set having this property?
You mentioned the Cantor set?
Yeah, I mentioned the Cantor set. Have you learned it in the first year? First
I
semester?
don't think so.
You have not seen Cantor set?
It's when you remove the open middle third from the interval and keep on doing that.
Right. So that way you get a set, right? So you look at intervals. So what is Cantor set? Look at the Cantor set. The usual Cantor set. You look at interval 0, 1. And what do you do? Next step, you remove the middle one third, right? Yeah. So 0, 1/3, 2/3, 1. Next step, you remove the middle 1/3 of both of them. And carry on this, right? So this is called this K1 is K2. So open set is removed, K3 and so on. And define K to be intersection of Kj, J from 1 to infinity. Yeah, have you seen this?
No, sir, we have never seen this.
You have never seen?
In our syllabus, we have never seen.
I know in your syllabus, there must be in your syllabus, right? So have you heard about perfect set?
No, sir.
Oh. So a perfect set is said to maybe let me give a definition of perfect set. So this you should learn in your first semester course. A set A is said to be say a subset of R. We call it subset of R only, but it's generally defined. Said to be perfect set if every well, if A is closed and every point of A is a limit point. So perfect set is a closed set which is on which every point is a limit point. So do you know an example? Yeah, example is whole of R, right? Closed interval AB, right? And then this set, this Cantor set. So the point here, the important point here, this K does not contain any interval. Every point of K is a limit point. And it is an exercise for those who are interested that K satisfies the property star. So this is an exercise. This is not for all, but those who are interested in mathematics. Exercise. K satisfies property star. So which means K is set of K is a set of measure 0. So once you know this this K satisfies star, then you define a function. So example continued. Fx is 1, x belongs to K, and 0, x belongs to 0, 1 minus the x at K. So the point of discontinuities is R. Okay, so the set of points of discontinuities is K. All right. So this function, so this f is Riemann integrable. So of course this exercise is for those who are interested. So if you can show this satisfies property star, then it is Lemma integral. And that is how you have to go. So this is a non-trivial example of a function where, okay, so one more thing here. K doesn't contain any interval, of course. K is uncountable. K is uncountable. So you look at your book by Bertel and Serbert, or there's a book by Charles Chapman Poog, Real Mathematical Analysis. You can find this nice exposition of contrasets. Yeah, any question here? Yeah. So read the. So what I suggest is in my lecture 6 there is a proof of this theorem. There is a proof of this theorem here. So you read the proof of this theorem, and we will have an interaction session particularly devoted to this proof, and of course this whoever interested can come. This is optional. Okay, so I'll let you know the timing. So proof is long, so it would be difficult to put it here, right here, in one class. So it is better, I mean, if you read it, then we can discuss. Any question? Yeah, so if there's no question, then I'll just stop here. We'll meet you tomorrow and we'll see the relation between differentiation and integration from tomorrow onwards. Okay.